the topic here is z-scores. And z-scores, we're going to be using z-scores throughout the course. We'll be using them in the next part of the course where we'll know the relationship between two variables. We'll have two variable statistics, and then also in the last part of the course when we do hypothesis testing. Z-scores, for this first part of the course, we'll be mainly using z-scores to compare data from different data sets, and also in some cases compute percentages. Anyway, at one point in time, the Scholastic Aptitude Test, SAT, had a mean of 900 and a standard deviation of 200. And at that time, the American College Test, ACT, had a mean of 25 and a standard deviation of 5. Now, these are two tests that colleges often use to decide which student to admit. Part A, Fran scored 1,300 on the SAT. How many standard deviations is Fran's score above the mean? There's a couple ways we can do that. The mean for the SAT was 900, so if we add one standard deviation, that's 900 plus 200, that's going to be 1,100. That's not going to be, we're not up to Fran yet, but if we add another standard deviation, that's going to be 1,300. So if we start from the mean and add two standard deviations, we'll get up to Fran's SAT score, which is 1,300. That way of computing works pretty well if you have for z-scores that are whole numbers. But if you have, sometimes people have z-scores that are fractions or decimals, and then it's going to be useful to have a formula to compute the z-score. And the formula that works is going to be the score minus the mean divided by the standard deviation. So this Fran's score was 1,300. The mean for the SAT was 900. Standard deviation is 200. So you want to do the subtraction first. So that's going to be 1,300 minus 900 is 400. And then do the division. 400 divided by 200 is 2. So Fran's SAT score was 2 standard deviations above the mean, or we can say that Fran's z-score is 2. Sandy scored 40 on the ACT. How many standard deviations is Sandy's score above the mean? Well, again, we can use the same formula, score minus mean divided by standard deviation. So Sandy's score was 40. The mean for the ACT was 25, and the standard deviation 5. So this is going to be 40 minus 25 is 15, divided by 5, which is 3. So now we can, with these z-scores, now we can compare Sandy's results with Fran's results, and we see that Fran had a higher z-score. Sandy had a higher z-score, so that means that Sandy did better compared to other students taking the same test. Sandy was 3 standard deviations above the mean, whereas Fran was only 2 standard deviations above the mean. If you only look at the raw scores, it looks like Fran scored higher, right? 1,300 is more than 40, but the tests were scaled differently, and so 40 on the ACT means a lot more than 1,300 on the SAT. Generally, z-scores of 2 or more are moderately unusual. That means both of these students did well on the test. They're both, Fran's score is moderately unusual, and Sandy's score is sort of a borderline outlier. Anything above 3 standard deviations or any z-scores above 3 or below -3, it would be outliers. So that's another way of determining outliers. Okay, so there's if we can also get percentages from these z-scores. Later in the semester, we'll be working with the z-table, which has additional percentages. Right now, we're just looking at a few percentages, but there's a whole table in the back of the book and in the course files that we'll be working with later. But for now, we're just working with a few percentages here that are related to the z-score. So, we're going to be working with the empirical rule, also called the 68, 95, 99.7 rule. And empirical rule is going to have 3 parts. Part 1 is the 68 is part 1, the 62 is the 95 is the part 2, 99.7 is the part 3. So part 1, that if you have a bell-shaped, or it's also called normal distribution of the data, then 68% of the data is within 1 standard deviation of the mean. In other words, 68% of the z-scores are between -1 and 1. And that's because the bell curve is symmetric, that means there's 34% on each side of the mean. And then the percentage under the entire bell has to add up to 100%, so that leaves 16% at the 2 tails. This example we'll be using empirical rule part 1. I assume SAT scores are normally distributed. In other words, they have a bell-shaped graph with mean 900 and standard deviation 200. Estimate the proportion of the SAT scores between 700 and 1100. We can compute the z-score for each of these z-scores here. So for 700, z is going to equal 700 minus the mean, which is 900, divided by 200. 700 minus 900 is -200, divided by 200 is -1. That comes up to be -1. And this one here, z is equal to 1100 minus 900 over 200. 1100 minus 900 is 200. 200 divided by 200 is 1. Okay, when the SAT scores are between 700 and 1100, that means the z-scores are between -1 and 1. And then we can apply empirical rule part 1. That means that the percentage of scores that are between those two numbers is going to be 34 plus 34, or 68%. Okay, empirical rule part 2. For bell-shaped data, 95% of the data is within 2 standard deviations of the mean. That's 47.5% on each side of the mean. That leaves 2.5% in each tail, because these have to all add up to 100%. So example 3, assume SAT scores are normally distributed with a bell-shaped graph with mean 900, standard deviation 200. Estimate the proportion of SAT scores that are less than 1300. So here we only have to compute 1 z-score. So that's z is going to be the score, which is 1300, minus the mean, which is 900, divided by 200. And this 400 divided by 200 is 2. Okay. So we want the z-scores that are less than 2. Well, there's 3 pieces of the graph here where they have z-scores less than 2. Right? Here's number 2. This is z-score 2 here, and it's going to be the 47.5% plus the 47.5% plus the 2.5%. So you want to add those up, and that adds up to 97.5%. So 97.5% of the SAT scores are less than 1300. Another way of expressing that, a z-score of 2 for a bell-shaped graph, a z-score 2 is in this 97.5th percentile. So it's another way of computing percentiles. Empirical Rule Part 3. 99.7% of the z-scores are between -3 and 3. That's 49.85% on each side of the mean. That leaves 0.15% on each tail. Example 4, assume SAT scores are normally distributed with a bell-shaped graph with mean 900, standard deviation 200. Estimate the proportion of SAT scores that are more than 1500. So again, we only have one z-score to work with here. Okay, so we want to compute the mean. So with probability of x is greater than 1500, it's going to be probability of z greater than 1500 times 900 over 200. And this is going to be probability z greater than 3. Okay, so this is so that's going to be the right tail here. That's going to be the 0.15%. 1.15% of the SATs are more than 1500. Okay, so let's summarize the empirical rule here. For bell-shaped distributions, bell-shaped data with bell-shaped graphs, 68% of the z-scores are between -1 and 1, 95% of the z-scores are between -2 and 2, 99.7% of z-scores are between -3 and 3. And this suggests that, at least for bell-shaped graphs, the z-scores more than 2 or less than -2 are moderately unusual. The z-scores more than 3 or less than -3 are outliers. So that gives the third way of determining outliers if the graph is bell-shaped. In fact, there's also a rule that applies to graphs that are not bell-shaped. The percentages are not going to be quite as high for between -1 and 1. The percentage is at least 0%. For z-scores between -2 and 2, the percentage is at least 75%. And between -3 and 3, it's 89%. But yeah, if you take additional statistics, you may get into if you take Math 251, they may introduce you to that inequality. Chebyshev's theorem is the one that applies there. And we just referring back to example 3 again. If you compute the probability of z being less than a number, that gives you a way of getting percentiles. For example, in example 3, we compute the probability a z-score of less than 2, and that was in the 97.5th percentile. So that gives us a way of additional way of computing percentiles and quartiles. And then later in the semester, we'll be working with z-scores that are fractions or decimals. There's a table in the appendix and also a table in the course files that has the percentages for z-scores that are fractions or decimals. Okay, so you can mix and match different parts of the empirical rule. Up to this point, I've only been working with one example at a time. One one part of the empirical rule at a time, but you can mix and match different parts of it. Example 5, again, we're assuming SAT scores are normally distributed with a bell-shaped graph with mean 900, standard deviation 200, and we want to estimate the portion of SAT scores, part A, between 700 and 1300. So again, we compute the z-score. The z-scores are between -1 and 2. The z-score for 700 is -1. Z for 1300 is 2. We actually computed those on the other page. So this is what the picture looks like. And for between -1 and 0, that's going to be 34%. That's from Empirical Rule Part 1. And then the z-scores between 0 and 2, that'll be 47.5% by applying Empirical Rule Part 2. And so if you add those two percentages together, 34 plus 47.5, you get 81.5%. So that's the percentage that are between those two. And then for the z-scores between +1 and +2, again, apply Empirical Rule Parts 1 and 2. If you apply Part 2, that'll give 47.5% between 0 and 2. That's a 47.5 for the other two. But that's more than what we want. We want to subtract off the part that's between 0 and 1. So I'm going to subtract off the 34%. So 47.5 minus 34% is give you a 13.5%. Okay, so that concludes this presentation.